Okay, I think it should be working now. I'm not sure. Microphone, speaker. Hello, hello, hello. Huh. Signal system. Hello, hello, hello. I'm not sure. Maybe I should use my phone. Switch to the phone audio. Sorry. Okay, hello, hello, hello. Hello. All right, so I'll just use this for the recording. And last time we said that yi follows independently exponential family with location parameter theta I, scale parameter phi. And the question is, what if the distribution has only one parameter? Then that's the location parameter. So we don't have this scale parameter anymore. Then related to, going back to the exponential family distribution, what happens is, if you recall, we write the density f of yi. It's frozen. Oh, okay. I see. Okay, now it's working. So if we write it as f of yi as exponential family, okay, as exponential family with exponential distribution with yi times theta I minus b function theta I, we talked about this, ai function of phi plus a c function yi phi. So in this form, if there's only one parameter, theta I, if only theta I is the parameter, which is the case for Bernoulli and Poisson, then we would have FYI reduced, as a reduced form. So the parameter phi is no longer a changing parameter. So then we would have it just as exponential with some yi theta I minus b theta I. Then here you would just have some parameter, some constant AI, I should say constant AI depending on the distribution plus some c function of yi, because the parameter phi is gone. So then you can see that for Poisson, for Bernoulli, they are of this simpler form. Okay, that's the random structure. For the systematic structure, last time we said that one way to specify the canonical, so-called canonical link function, is to specify the linear predictor, which is denoted as eta I, which should be some transformation of G of the expectation of yi, okay, which is typically denoted as mu y. So we will often write this as G mu y, just for notation. And this transformed GEYI, called eta I linear predictor, just write the name here, is supposed to be a linear function of predictors. And in the form of canonical link function, we set eta I to theta I. Okay. And then we can show that this is just the first derivative, the inverse of the first derivative of b function applied to, applied to this mu I. Okay, mu I is this one. So we actually have this directly. This is how we specify it. So in other words, this will give us G function. It's just the first derivative of B inverse. Okay, and then the systematic structure assumes, so this is basically, there are two things we assumed. First is that eta I equals theta I. This is what we assumed for this part. And then by definition, as linear predictor, eta I is set to xi transpose beta. So that's why it's called linear. It's because it's a linear function of predictors. And by assuming eta I being theta I, then we have a specific form of G, which is the inverse of B prime. And we call this canonical link function. So that's the whole logic. So ideally, or I would say the use of this is that for any distribution in the exponential family, as long as you write its probability density function or its probability mass function in this form, and you recognize what is the B function, then you know the form of the B function, and you take the derivative and take its inverse. That will give you the link function. So the logit functions we gave for the logistic regression, where the distribution is Bernoulli, is exactly the canonical link function. And later, when we talk about Poisson regression, where the distribution in the random structure is Poisson, with only the location parameter, we can show that the canonical link function is the log function with a natural base. Okay, so that's what we did last time. And then we can say that given the form of the canonical link function, and given the form of the exponential family with the use of canonical link function, we can actually have the likelihood of beta written out. So I would just, because this is a review, the log likelihood of beta, given the canonical link function, can be written as, we use the small l for log likelihood at beta. So last time we said it can be written as the summation over my observations. This is my response, yi, times xi transpose beta, minus the B function at xi transpose beta, divided by ai phi, plus C function at yi phi. So this is the log likelihood. And then our goal is to find the beta value that maximizes it. So it then became an optimization problem. Okay, so then the question we left at the end of the lecture was how to maximize this log likelihood by searching for beta. And please note that here beta is a p-dimensional vector. Okay. The first element is the intercept. The remaining are the slopes. So last time we talked about the Newton-Raphson optimization. So Newton-Raphson optimization is because of Taylor expansion on the gradient. That's the essence of it. So the reason is that we want to set the gradient of the p-dimensional, this f function is defined in the p-dimensional domain and has real values. So our goal is to find beta star as the maximizer, which we call it argmax of beta, of f at beta over beta in RP. That's our problem. So we are just generalizing this optimization problem for any function f. So in our case, the function f is the log likelihood. And the Newton-Raphson, we call that NR method, is by Taylor expansion on the gradient of f. So we are basically saying that the gradient of f at beta can be approximated by the gradient of f at the current value beta 0 plus the second derivative in the matrix form is the Hessian matrix at beta 0 times beta minus beta 0. So everything here is vector or matrix, right? So especially these, this is P by 1, P by 1, this is P by P, and this is P by 1. That's the dimensions of these terms. And the reason we do this Taylor expansion is that the gradient itself in the exact terms may be very complicated. Then setting the gradient to 0, it may be difficult to solve. So therefore, we're not setting the gradient to 0, but we're setting the approximation to 0 to solve for beta. So basically, setting the right-hand side, show that RHS, setting the right-hand side to H0 gives us an update. The update is just, we can have as the next beta value is equal to beta 0 minus the inverse of the Hessian of f at beta 0 times the gradient of f at beta 0. So this is how we solve the right-hand side, set it to 0 and solve for it. And this gives us an update rule. So the update rule at iteration B gives us the next value. I will call that beta t plus 1 is actually the current value beta t minus the Hessian matrix at beta t current value inverse times the gradient f at current beta t. That's how we do the update. Yes. So are you asking why we want to set it? So it's just the algebra, right? So if I would just write one more step, if I set this to 0, maybe I just grab a different piece of paper. So if I set this to 0, it's just, let's see, beta 0 plus Hessian f beta 0 times beta minus beta 0, set it to 0. Right? It's algebra. We move it to the side, so then we have HF beta 0 times beta minus beta 0 equals to negative gradient beta 0, right? And then we multiply the inverse on both sides. So beta minus beta 0. Yeah, so we make the negative sign outside. Okay, and then we move the beta 0 to the right-hand side. Right? Okay. Yeah. So so actually, so when you have this question, it's because I'm just curious about like where is the missing gap? Is it because you didn't do the derivation or you didn't know how to do the derivation? I want to make sure. Oh, I see. Okay. Yeah. Okay. So that's how we get this update. Thank you for the question. All right, and then that's it. That's the Newton-Raphson. But what this means is that at every iteration, you need to compute two things. One's the gradient, one the Hessian. You need to compute both, right? So when Ron Fisher, developed the Fisher scoring method, so we'll call this FS method. What we did is that we actually used the fact that F is the log likelihood. Okay, that's the key thing here. So therefore, we would replace this Hessian by the expected Hessian. So in this way, so basically what's changed is that change the Hessian matrix of our log likelihood. So we use the log likelihood. So I will say here the F beta is just our log likelihood at beta. So we change the Hessian of the log likelihood at beta to the expected value of the Hessian at beta. That's the major change we have. Now I have a question for you guys. What does the expectation refer to? Expectation of what? I think this is the crucial part because it's hidden in the writing. It's not explicit. Therefore, I want you to think, when we write expectation, we always consider random variables, and we're taking an expectation of random variables. Then what are the random variables? The what of the Hessian? Each entry of the Hessian, but where is the randomness in each entry of the Hessian? What is the random variable? Sorry. yi, yes, y1 to yn. Yeah, this is the key. If we scroll back to the log likelihood, the formula, even though we consider it to be a function of beta, but you actually have y1 to yn involved. And y1 to yn are the only random variables in this function because xi's are considered fixed. Okay, this is very, very important. Otherwise, you will get confused about what is expectation actually for. Okay, we change it to this, and then the update. So then the update would become what? So if I still use update at iteration t, it will become beta t plus 1 equals to beta t plus the expected of the Hessian of the log likelihood at beta t. Yes, inverse times the gradient of log likelihood at beta t. This is what we will do in Fisher scoring. Okay, and then one more thing, what I need to introduce is that for log likelihood, we have some specific names for the gradient, and we have some specific names for the expected Hessian. What is that? Okay, so first of all, now we have some definition. So we define two things. First, we define the Hessian, we define the gradient of the log likelihood at a particular beta value. We call this score function. So in statistics, you will see this term score function appear in many places. And the score function is denoted as S beta. S stands for score. Okay, and the score function has some very interesting properties, and I will detail them very soon. But before we do that, let's define the second concept. The second concept is the expectation of the Hessian of the log likelihood at beta. And we give this a name. Actually, I should say it's the minus of that. Yeah, minus of the expectation of the Hessian of beta. This is given the name as Fisher information, named after Ron Fisher, and this is denoted by I at beta. I stands for information. Okay, I don't know how many of you have heard of Fisher information before. It should be some, right? It should be some of it. I think in the undergraduate mathematical statistics, you should learn this concept before. If it's like one-dimensional, if beta is just a scalar value, it's easier to explain. So maybe I'll just use the other piece of paper to give you some intuition of the Fisher information. So if it's just one parameter, so if beta is R, okay, then the likelihood function can be written, can be drawn maybe in this way. one-dimensional. So if the likelihood function takes a shape like this, so the likelihood, given your data, your y1 and yn are from your data, you vary the beta value, you evaluate the likelihood. Then if we can draw a figure like this, where is the maximum likelihood estimator? It should be where the likelihood is maximized, and you go back, and the corresponding beta value here is the beta hat MLE. That's the idea, right? We find the beta value to maximize the likelihood. So it's called maximum likelihood estimation. And if it's a function like this, the global maximum is the only local maximum. Then by setting, by setting the derivative of likelihood to beta, I'm still using the gradient notation, but it could be just the derivative. By setting this to beta, setting this to 0, we can actually show that the beta hat MLE is essentially where the gradient is equal to 0. First derivative 0, it's flat here. Then what does the second derivative mean? So this is a calculus problem. Let me ask you, the second derivative at here, is it positive or is it negative? Negative, right? It's negative. So we know that if I just go back to the normal notation, L prime beta hat MLE, because it's one-dimensional, is 0. Then L double prime beta hat MLE, it's negative, right? So that's why in the definition of Fisher information, we are taking negative sign of the second derivative. So the Fisher information at beta is defined, in this one-dimensional case, defined as the negative expectation of the second derivative of log likelihood at beta. Again, here the expectation is taking over our data. So you can see this is negative. Then let me ask you, what is Fisher information at beta hat MLE? So it's about the absolute value of at the beta hat MLE after, sorry, I should say that because it's negative, so taking the sign, taking the negative sign give us the absolute value. Then this negative beta hat MLE is called the curvature about how curved this part is. So I can share with you another kind of plot. Let me just draw another one. So suppose that is also the log likelihood, but it looks like this. We have a very narrow sharp peak, and this is where the beta hat MLE is. So let me ask you one question. So if I compare the second derivatives for these two curves, and I multiply both by a negative sign, so they become positive, which one has a bigger value? The left one, right? So this is like more curved, more sharp, so it has more value, has a bigger value. And then by the definition of Fisher information, if we ignore the expectation part, because expectation is like average across data, just look at this one curve alone, the Fisher information here will be bigger. Yeah, so that's why it's called more information. Fisher information being bigger, what it implies is that to help you find the MLE, the beta value, the data on the left-hand side versus the data on the right-hand side, because your likelihood will be based on the data, right? So you will get a log likelihood. And then expectation is taken over other possible data from the same distribution. It's an average. So it's telling you that given a distribution like this versus a distribution like this, the left one provides more information for estimating beta from data, because you have more certainty about where the MLE is. And you can imagine a more extreme case in which you have the beta and log likelihood beta like flat. In this case, there's no way for you to know where the MLE is, right? So then you have very little information, almost no information for estimating beta. So that's the intuition behind Fisher information. Why do we call information? Here, the information is about estimating beta. Does that make sense? Okay. So then, in the matrix form, this negative expectation of Hessian matrix at beta is called Fisher information. All right, so that's the two definitions. Now, we are going to look at the score function. So if we use the score function, by definition, as the gradient of the log likelihood at beta, then let's go back to the definition of log likelihood. Let me just put down the definition of log likelihood. It's the log of the likelihood of beta. And also recall that when the yi's are independent, the likelihood is just the product of yi's densities, right? So when the yi's are independent, this is a key assumption. Otherwise, we cannot factorize the joint density into the product. We have this as log of the product I from 1 to n, f of yi given parameter beta. So this is just the definition of the likelihood. And because we know log of the product becomes sum of the log, then this becomes summation I from 1 to n, log f yi beta. Okay? Any questions so far? No. Then we move the differentiation inside the summation. So we get I from 1 to n derivative of log f yi beta. Okay, now we'll use the chain rule in calculus. When we take the differentiation of log of a function, so we will take first derivative of log, right? It becomes like the inverse. Yeah, So we will have like 1 over the f. And then we need to take derivative against f. So we have f prime, right? So essentially, this becomes summation I from 1 to n f yi beta f prime yi beta. Okay, this is the score function. We basically, for any log likelihood, this is the general form. It's not specific to exponential family. We haven't used exponential family formula at all, just general. Any questions so far? No. Okay, so given this derivation, now we have something nice. The nice thing is that the score function has a nice property. We can show its expectation. If we add expectation to the left-hand side, to the right-hand side, expectation is for y1 to yn, as we just said. It's actually equal to 0. So we have that. And also, we can give this another name. So for the last term, we can write it as, we can denote each term, the ratio, we can give it a name. So we can call it I from 1 to m fi beta. So this is just a notation definition. So essentially, we define this ratio term to be si beta. That's how we define it. So we can just simplify it a little bit in terms of notation. So when we write it out, we don't need to write the ratio again and again. We just write si beta. So the important property about the score function, the gradient of the log likelihood. Oh, by the way, I should say what I'm talking about here is the foundation for log likelihood, for the likelihood ratio test, which we already gave you the result. The likelihood ratio test statistic, -2 times log that likelihood ratio, right? It's the likelihood ratio of the likelihood under null over likelihood under alternative. That thing follows chi-square distribution, whose degrees of freedom is the difference of parameters between the two models. So that asymptotic distribution can be derived using what I'm saying here. So basically, what I'm saying here will be a way to derive the asymptotic distribution for the likelihood ratio statistic. using Taylor expansion. So that's why you will see that we're working on the first derivative, second derivative for that reason. Yeah, I'm just trying to draw the connection here. And you see that the score function is introduced for a reason. Then, given the score function, the property, what I just said by words, is that expectation of this S beta is 0. And please be sure it's a 0 vector, p-dimensional, since the score function is this is p-dimensional. Don't forget about the dimension. Okay. And also, even though here each f, I mean the f density is a scalar, is actually a scalar value, but what's happening here is that you are having f prime on top of it, right? So this f prime, to be exact, I think this is just an abuse of notation. To be exact, I should write this. It's the gradient of f for beta. So be careful. It's the gradient of f for beta. So that's why the denominator is a vector. It's not a scalar. The numerator is a vector. The denominator is a scalar. Yeah, we should be careful about dimensions. So this is p-dimensional 0 vector. How do we prove it? And the proof, again, involves changing differentiation and expectation or integration. So we're putting what we have from here. Expectation of S beta is just, I put this expectation around it. I can move it inside the summation. I from 1 to m, expectation of the numerator as gradient f yi beta, f yi beta. Okay, and now we are going to use the definition of expectation because it's the yi, that's the random variable, it's expectation with respect to yi. So therefore, changing it to the definition of expectation as integration, it's basically integration of, I changed the notation of yi to small value, small notation, lowercase yi, because I want to say that now I'm considering different values this random variable yi can take. And then I consider the density of different values. And that density is just fyi beta. Byi, right? This is the definition of expectation. And then, of course, you can see cancellation, right? This and this get canceled. I'm only left with a gradient term. Now I move the gradient and the integration. So it's move the gradient out. It's integration of fyi beta byi. And of course, this is known to be equal to 1, right? If it's 1, we take derivative, and this derivative is against beta, we get 0. So that's how we prove it. Okay, so for this property, we'll see how it can be useful for other uses. And also, we can similarly prove not just this S beta has expectation 0, but what we have over here for Si beta, the elements inside the sum, they also have expectation 0 by the same proof. Okay, and this is also 0p, p-dimensional. Okay, that's for this. And then for the score function. Now let's look at the Fisher information. For Fisher information, let's first look at the action of the log likelihood at beta. As you know, this is a P by P matrix. So what are we going to do is that we're going to take another derivative against beta from the score function. from S beta. Let's take derivative against beta once more. So recall that we are already here. S beta is equal to this. Okay, then from here, let's continue. So given this S beta being this term, we continue to derive the Hessian. So what happens is that, you know, when you take the derivative of a ratio, you know the formula, right? So you need to square the denominator. You take derivative of the numerator times the denominator plus minus, you take the, you keep the numerator times the derivative of the denominator. So that's the formula. So here, this can be shown as, I'll just write out the result, differentiation result, I from 1 to m. Okay, and the denominator, because it's scalar, we just square it, f squared yi beta. Numerator, we first take the derivative of a numerator, which is a gradient itself, then we take it again, it becomes a Hessian. hf yi, sorry, let me see. Yeah, the density, yes, HYF yi beta. Yeah, but be aware that when we say the Hessian, it's against beta. So it's a P by P matrix here itself. And the denominator, the scalar stays, so I put it in the front. Okay, and then minus. I keep the numerator, I take the derivative of the denominator, so then it becomes gradient times gradient. And I need to be careful with the dimensions because here I need a P by P. And each gradient is what? The gradient is P by 1. So I have the gradient times the inverse, times the transpose of the gradient. Okay, P by 1, 1 by P, I get P by P. All right, and then this is the Hessian. Now let's look at Fisher information. Then we can see why for the log likelihood function, the expected Hessian can be a simpler form than the Hessian. So that's why when we use Fisher information, instead of the negative Hessian, we simplify it. So let's look at expectation of the Hessian of log likelihood at beta. So you see that it's expectation of two terms. I will show you. I can put it inside as expectation of the first term, f squared yi beta, f yi beta, Hessian f yi beta. That's the first term, minus expectation of the second term, gradient f yi beta times the transpose gradient f yi beta. Okay, so I just separate the expectation into two terms. And then I'm going to show you the first term is actually 0. And then I'm left with the second term. Okay, so we can show that the first term, expectation of this, fyi beta, Hessian f yi beta. Okay, again, by definition, we use integration. So it's again integration of this term. I change yi to lowercase to mean any value the random variable can take. Okay, and then times the density. dyi. Okay, so you see that now I have cancellation again. These are canceled. So it's just the Hessian yi beta dyi. And again, if I change the overall second order derivative and the integration, I get 0 again, right? Because it's just like, I can say, how do I use the notation? It becomes like this, f yi beta dyi. Maybe I just move one of them outside like this. So I'm taking the gradient and another gradient again. So basically I'm saying that if we know already with the integration of gradient f is 0 from the previous result, then it's for sure 0. So this is just 0. That's for the first term. Then I only need to worry about the second term. What is the second term? Then you can see that that's something very nice. So as I said, the Fisher information, then the Fisher information we call I beta is defined as the negative I'm sorry? How does H what different from H what? Okay, this is the Hessian of the log likelihood, and this is the Hessian of the density function, but they are both with respect to beta. So the log likelihood is the summation of log f. Yeah, but this is the Hessian of the f. So f as a density function involves both yi and beta, and we're taking the Hessian of f against beta. So that's why this is also a p by p matrix. And I should say that when I write 0 here, it's a 0 p by p 0 matrix dimension-wise. Okay, then the Fisher information defined as expectation of the negative expectation of the Hessian of log likelihood. Now we're only left with this term. Negative sign is gone, right? So it becomes just what? Just expectation of this. And now I can write it in two terms. I can write it as gradient f yi beta. Please note that all the gradients here are against beta over f yi beta. The denominator, as I said, is scalar times the own transpose. Its own transpose. That's it. And recall that on the previous page, we'll have defined this ratio to be SI, right? Remember the notation SI here. Then this just becomes, I forgot the summation sign. The summation sign needs to be outside this one, I from 1 to n. Yeah. So then it's the summation I from 1 to n. Inside expectation, I have SI beta times SI beta transpose. Okay. First term, again, P by 1. Second term, 1 by P. That's the Fisher information. So you see that we are linking Fisher information to the, I forgot this one, negative. Yeah, I think I'm right. We link Fisher information to scoring function in this way. Please note that Fisher information is expectation. So y1 and yn are gone after expectation. But scoring function is not expectation. We still have y1 to yn involved. That's the key thing. So here I want to say that there are no more y1 to y1 to ym. So they are basically integrated out during the expectation. But in the SI part, we still have y1 to yn involved. So we should be very clear about that. Okay. And furthermore, I will go one more step. Remember, we talked about that variance formula. We said that the variance, we had the variance of a random variable is equal to the expectation of the variable square minus the square of the expectation of the random variable, right? That formula we will use again here. So then this term inside the summation can be written as the covariance matrix. I'll just use the variance as the variance covariance matrix of SI beta. This is a p-dimensional random vector. This variance covariance matrix is p by p, just as the one we have for beta half, if you remember. Variance of beta half is a p-dimensional covariance matrix. This plus the expectation of SI beta, which is p-dimensional as well, times the transpose of expectation of SI beta. Okay, we are using that formula again. And now the property that the score function has mean 0 comes in. So this is basically 0, and this is also 0 transpose, right? So we get a 0 matrix here. So therefore, we have this just equal to summation I from 1 to n, variance covariance matrix of SI beta. That's it. That's the Fisher information. So the key thing is this. As long as we could compute SI beta, and we could then get the Fisher information. And just as a recall, we basically recall that SI beta takes this form. So the numerator is a gradient. The denominator is a scalar. Okay, any other questions? Yes. Yeah, so basically from here, from this property down here, we already showed that when you just have one derivative, it's the gradient, you integrate that, this is 0. You already have that. And they are taking another derivative, then it stays at 0. Yeah. Yeah, but just for your information, mathematically, whenever we swap integration differentiation, we need the function to be smooth. That's the key thing. Yeah. So that's why exponential family, which specifies our f function, density function, is a good function, right? For exponential family, their density functions are smooth. And okay, so we have everything. Basically, we just need a Fisher information to do our, need a scoring function, we need a Fisher information to do our update. So let's come back to the Fisher scoring here. You see, the update will be like this. Here's the update we need. Then if we want to use what we just calculated, then the update of Fisher scoring method is, we just change our notation, nothing special. It will become beta t plus 1 equal to beta t. We set it to beta t minus, because here we have plus. Now we're going to use Fisher information. Fisher information at beta t inverse. Scroll up a little bit. Inverse times the scoring function at beta t, because we defined the gradient, the log factor scoring function. So we're just changing everything to our new set of notations. Okay. And if you go one more step, you're going to replace this Fisher information by this formula, the summation of the variance covariance matrix of the score of the SI, the ith item in the scoring function. Okay, so then let's look at basically, before we finish today, I will just quickly show you a derivation for logistic regression. So for logistic regression, this is what we can have. Just piece of paper, biggest note. So in the logistic regression, the log likelihood, if you tried it using the canonical link function, which is the logit function, what we could have is from this exponential family distribution. Let me quickly grab that here. This is from our last lecture, the log likelihood, and we know because we said eta I to theta I, and then eta I is here to replace theta I in the exponential family density function. And then as eta I is xi transpose beta, we introduce beta. So xi transpose beta is here. Basically, beta is involved in the two terms in the numerator. And then, if we come back here, we have the logistic regression. We express it in terms of the exponential family form. So this is the B function we end up getting. Okay, that B function. But we'll have xi transpose beta here and here. Then when we take the score, when we calculate score function, it's the gradient of the log likelihood against beta. This is what we get. Summation yi xi. Okay. What is the dimension of this? P-dimensional, because xi is a p-dimensional vector. Don't forget that. So y is a scalar. This is p-dimensional. Okay. And for this term, we just take derivative. So 1 plus exponential term in the denominator. This is a scalar. And this is the derivative of 1 plus exponential xi transpose beta. 1 is gone. Exponential stays. And then against beta in the exponent, xi comes down. So in here, in the numerator, xi is a vector. So that's why we have a vector here. So this is our P. And then we take Hessian once more. When we take the Hessian, we take derivative against beta one more time. And the first term is gone since it no longer involves beta. And then the negative sign comes to the front. It's over here. And we square the denominator, so we get a square. Then we use that calculus again. We take the derivative of the denominator, multiply the numerator. That's what we get for the first term. Okay, this one stays. We take the derivative of the denominator minus this one. Right, we have the first derivative. We have this one. How do I say it? We have this one taken derivative again. So we have another copy of it, and xi comes down. So because we need to make sure that this is a matrix form, so this first term is p by 1, second term transpose is 1 by p, and this is a scalar, it stays. So essentially, you will have this term as a p by 1, this one 1 by p. So they are the same term here and here. So that's how we get a Hessian. And then from here, you take expectation. But the good thing here is you don't need to do anything for this expectation. The reason is if you check this Hessian, your y1 to yn are gone. So it only involves xi and beta. So it's not random anymore. So its Hessian is just its expectation. Okay, and then in this case, the Fisher scoring is just equal to Newton-Raphson because expectation doesn't do anything. Okay, so that's how we finish here. So in this class, we just finished talking about Fisher scoring. The two key concepts I hope you can understand now. One is score function, which is the gradient of log likelihood. The other is Fisher information, which is the negative expectation of the Hessian of log likelihood. So, you know, we work with log likelihood instead of likelihood because of exponential family density. That's the special thing. Okay, so that's all for today. Then I will see you on next Monday.